All right, let's check out page 403. Yesterday we were practicing the second fundamental theorem of calculus. It's the idea of taking the derivative of an integral, which are kind of inverses because they cancel each other out. But in doing that process, sometimes we got back the original equation, sometimes we didn't. It all depended what the bounds looked like. Okay, remember, taking the derivative of an integral cancels each other out, but we still have to do the kind of top minus bottom first fundamental theorem rule, but continuing to multiply by the derivative of those bounds. So we're going to do some more of that today, but instead of just practicing the concept like we did yesterday, we're going to see how that second fundamental theorem might pop up kind of in like free response or graphing type questions. So we're going to do a bunch of graphs today to kind of help this idea sink in a little bit more. So off to the right here, they give us the graph of g of t. I always like to label kind of what's going on. So that's the graph of g of t, but they also give us the function f of x. And notice how f of x is defined as an integral, aka an antiderivative, specifically of the g of t function. Now we don't have a g of t function, but we do have a g of t graph. So maybe we can use that to our advantage for some of these questions. So for the first one, we want to find the value of f of 0. Don't overthink this. What does this 0 represent? An x value, okay? And specifically, we're going to plug in x into the f equation for every x that there is. So notice at the top, they give us the f equation. If we were to plug in 0 for every x, the integral would change from bounds -4 to 0. Because wouldn't we plug in 0 for x in that top bound? So by plugging in 0 for x, you're actually choosing what top bound you wanted. 2 times 0 would give us 0. So f of 0 is the area under the g graph from -4 to 0. Now I'm saying the g graph because that's what they gave us. So if we look at -4 to 0, we want to figure out all of that area. Can we maybe break it up into different shapes to help us do that? How might you want to find the area? Yeah?
Ignore the little two triangle parts because they cancel.
Okay, so this triangle, which has a negative area, would cancel out this triangle of the same shape that has a positive area. So we just basically got to figure out this remaining area. And if you section it off into familiar geometric shapes, it looks like we have a rectangle we need to find and a quarter of a circle. So area of a rectangle would be base times height. And then for the quarter circle, we need 1/4 pi times the radius squared. Looks like the radius would be 2. So 2 plus pi, looks like. There's the value of f of 0. Do you guys think you can do number 2? Kind of a similar question. This time we want to plug in 2 for every x. So in terms of the integral, that would make the upper bound 4. Anybody get it? You good, CB?
4 plus 8 pi.
How'd you get 4 plus 8 pi?
Hopefully not incorrectly. But I did the.
I like the
I did
4.
A rectangle and then a half circle.
So which rectangle? This whole rectangle?
The whole one.
The whole one?
Yep.
So that would be 4 times 1, which is 4. And then you did a half circle, 1/2 pi times the what was your radius?
Oh wait, that's why.
Okay.
4 squared, not 2 squared.
2 squared. Okay. Good. So that would be 4 plus 2 pi. Okay, I like it. So Stevie, I think, noticed again how the 2 triangles on the end would cancel each other out. Okay. Maybe some of you noticed that going from -4 to +4 is just doubling the area that we found previously. Did anyone check that out? So if you double 2 plus pi, you get 4 plus 2 pi. Thank you. Okay. How do we do with number 2? Pretty good? All right, let's check out 3. So a little different for this one. Find f prime of 1. So this time they're asking us to take a derivative and then find a value. So if we take the derivative of the left-hand side of f, which we could denote as f prime, we also have to take the derivative of the right-hand side. What you do to one, you do to the other. Notice how the right-hand side is an integral, though. So we're taking the derivative of the integral. We're going to go ahead and use that second fundamental theorem of calculus. Can someone describe how that worked from yesterday? How do you take the derivative of an integral? What do you think, Joseph?
You plug in the top
Oh.
to
Into the function.
yeah.
So if we plug in 2x, that would be g of 2x.
And then you multiply by the derivative.
Derivative of that bound, which would be 2.
Then you subtract
Mm-hmm.
the same thing to the bottom.
There we go. Subtract, plugging in the bottom bound, so that'd be g of -4, times the derivative of the bottom bound. The derivative of -4 is just 0. So there's a little shortcut maybe that we might be able to use from here on out. Whenever you're taking the derivative of an integral, whatever bound is just a number, you could automatically put 0, because isn't that eventually going to be times 0 anyway? Okay, so that's just going to go away, but I know some of you like to write it down just to see the work, but maybe that's a little shortcut we can use. So it looks like f prime of x is g of 2x times 2. Now they're asking us to plug in 1 for the x, so we got to figure out the g of 2 value and then double it. How might we want to do that? Look at the graph. They give us the graph of g. So we're going to plug in 2 into the graph. Looks like we get out 1. And if we double 1, we get 2. So f prime of 1 is 2. Since it's positive, we know the f graph is increasing, even though we don't have the f graph because they gave us the g graph. But nonetheless, we found the value. Do you think you can try 4? F prime of -2? What do we get? Anybody confident? Yeah? -2, good. All right, so we have the first derivative of f at the top, or number 3. So if we plug in -2 for x, that would be g of -4, and then we need to double that. G of -4 based off the graph is -1 times 2 is -2. How'd you do? All right, let's try another derivative. Okay, f double prime of 2. Let's go ahead and perhaps rewrite the first derivative to help us out. Instead of having the times 2 on the end, we're used to having a coefficient be in front of a function. So maybe we'll write this as 2 times g of 2x. So if they're asking us for the second derivative, let's take the derivative of g, or 2g of 2x. How might you want to do that? Think about your derivative shortcuts or your derivative rules. I know we've been doing integrals for a while, but we still are talking about derivatives. Can we think about it? Let's see, the 2, you want to give it a shot, Joseph? Go ahead. Are you sure? You thought about it. Still no? Okay. So the 2 is a coefficient. We can go ahead and keep that. How can we write the derivative of g? You want to give it a shot, Dan?
You could take the top exponent, which would be 1, and then multiply by the 2 and then decrease it. Right?
You mean like that?
Yeah.
So, okay, so if you brought the 1 down, that would bring 2. And then we'd have g times 2x to the 0 power. That would just go away and we really wouldn't have a function left. I don't know if that's going to work. How can we write the derivative of g? Yeah? G prime of 2x. But we have an inside, kind of like our chain rule, times 2. Remember our chain rule? Derivative of outside, keep the inside, times the derivative of the inside. It's been a while. Okay, so there's our second derivative. Let's go ahead and plug in 2. All right, so we got to figure out g prime of 4. What should we be looking for on the graph of g? The slope at the x value of 4. So we're looking for the slope at that point. What is the slope at that point? Be careful, yeah?
-1?
That's what everyone thinks.
No.
Yeah?
It's an endpoint, so it doesn't have one.
It doesn't have a slope. Isn't it an endpoint? Remember, derivatives or slopes don't exist at sharp points, endpoints, vertical slopes. A little tricky, okay? So if you were to pick any other point on that line, Joseph, that would be -1. But the fact that it's an endpoint means a derivative doesn't exist. So, since this is an endpoint, the second derivative of f at 2 must be undefined because the slope, or g prime of 4, doesn't exist. All right, that was kind of an intro question. We're going to do a bunch more of these today and most likely Monday because we have quite a few to go over. But they're all very similar, okay? They're going to be asking us for different function values given a graph. All right, let's try the next one. Given the graph to the right, this is f of t. 3 line segments and a semicircle. Additionally, the function g is defined to be that integral. Notice how it's very similar setup to before. They gave us a function, which happens to be an integral, but then the graph is of a different function. All right, let's try the first one. Find g of -6. So in the g function they give us, we'll go ahead and plug in -6 into the x, which happens to be the upper bound. How might you want to find g of -6? let's first take a look at the integral. Do you notice anything kind of weird about it? It's what's backwards. That's good. The order. We normally have the lowest number written first. No, but notice how the lowest number is actually the top bound. So if we reverse the bounds, remember that property for integrals, what happens? If you switch the bounds, it becomes a negative. It's that opposite. Right. So we got to figure out the area from -6 to 1. And then we got to take the opposite of that. So it looks like we have a triangle, but then also a trapezoid. All right, so the triangle, 1/2 base times height. And then since the trapezoid is below the x-axis, this is a negative area, so we'll subtract that value. We have 1/2. The height is 2. Sum of the bases, 3 plus 2. Let's see. So 4 minus 5 would be -1. But then we have that negative out front because we switched the bounds. So that would give us +1. Can you guys try number 2? Find g of 6. If we plug 6 in for x, that's going to be our new upper bound. The bounds are okay for this one, right? We don't have to switch them. Okay, so graphically, we're looking for the area under the f graph from -1 to 6. Let's see, the trapezoid's underneath the x-axis, so it needs to be negative. And then we got a quarter circle above the x-axis with a radius of 2. -8 plus pi. Can we get that? Sound good? All right, let's check out 3. Find g prime of 6. Okay, so let's first just tackle the derivative. They give us the g equation at the top, so we want to take the derivative of that. But notice how we're taking the derivative of an integral. So that's the second fundamental theorem of calculus. We'll go ahead and plug in the top bound, which would be f of x, times the derivative of the top bound, which would just be 1. And then we got to subtract, plugging in the bottom bound and all that jazz, but notice how the bottom bound is a number, so we'll eventually be multiplying by 0. So it looks like this is our first derivative of g. Let's go ahead and plug in 6. So the first, or g prime of 6 is actually the same as f of 6, which is what value? Right, this is the graph of f. Maybe you don't want to label it as f of t. We'll just say graph of f. Let's try the next one. If we want to plug in 2 into the derivative of g, That's the same as evaluating f of 2. Which is, looks like -2 based off the graph. We doing okay? We ready for a second derivative? All right, so second derivative of g. Let's go and reference that for a second. So we have the first derivative written in number 3. If we take the derivative of the left, that would be a second derivative of g. What about if we took the derivative of the right? How can we write the derivative of f? And that should just be f prime. Okay, so if we plug in 2 for that x, we have to plug in 2 for this x. What about f prime of 2? The slope of the f graph at the point of 2. Can we find it? If you were to plot a point at 2 and draw a tangent line, what would the slope look like? Why not? It's a sharp point, right. I can draw a tangent line like that. I can draw one a little shallower, maybe a little steeper. Okay, there's not just one tangent line that can touch that point. So that if you have multiple slopes, there's no way you can actually define it as being one slope or one derivative. That's why we have that sharp point there. So we'll say it does not exist. They want us to give a reason because f of 2 is a sharp point. Let's try 6 because it's kind of similar. We're going to plug in -4 into the second derivative of g, but that represents the first derivative of f, aka the slope of the f graph. So what's the slope at -4? Plot a point, draw a tangent line. What does it look like? Maybe you want to pick a point before it and after it to help you out. Do you rise over run? What'd you get? Good. It's like pulling teeth today, guys. We got -2. Give a reason for your answer. Because the slope of the f graph is -2 at the x value of -4. Alrighty, let's try another one. Alright, so they give us a graph. They tell us it's the graph of f. It's continuous from -4 to 3. The graph consists of 2 quarter circles and 1 line segment. And the function g is defined as 1/2 x squared plus an integral. So a little different. We have a little extra piece in there. Find the value of g of 3. Do you guys want to do that? That was a rhetorical question. Go ahead and give it a shot anyway. We're going to plug in 3 for all the x's. Let's see, what'd you guys get for the area from 0 to 3? 0, right? We have the same amount of area above as we do below, so the value of that integral portion is 0. So it looks like we're just left with 9 over 2. Let's try the next one. We're going to plug in -4 into g for all the x's. Anything look weird? Different? Take a hard look at it. We got to flip it, right? Because the lowest number is actually the upper bound. So if we flip the bounds, it becomes negative, which means it looks like we'll be subtracting that integral. Let's see, -4 squared is 16 divided by 2, we got 8. So 8 minus that integral. -4 to 0, we have the first quarter circle plus the second quarter circle. Let's see, so I got -1/4 pi for the little circle, 9/4 pi for the larger quarter circle. Added together, that would be 2 pi. So we have to subtract that because we switched the bounds. Doing okay? So far? We'll go ahead and throw in a derivative question. Find the value of g prime of 3. Let's go ahead and just tackle g prime first. So they give us the equation of g. We got to take the derivative of each piece all the way through. Let's just first tackle the first term. Derivative of 1/2 x squared. Can we do that really quick? I think that'd just be x. And then we need to add the derivative of an integral. Okay, second fundamental theorem of calculus. So plug in the top bound times the derivative of the top bound, which would just be 1, minus plugging in the bottom bound times the derivative of the bottom bound, but notice how the bottom bound is 0, so it's going to go away anyway. Derivative of 0 is 0. So there's our first derivative of g. We want to go ahead and plug in 3 for all the x's. What's f of 3? Negative 3, we're going to use the graph at the top because that's the graph of f. You plug in 3, you get out negative 3, so it looks like in the end the derivative of g at 3 is 0. What does that mean about the graph of g? Even though we don't have the graph of g? Can we be a little analytical? I know they're not asking us to justify or explain anything, but what can you tell us about the graph of g?
It's a max or min.
Possible max or min. Yep. Possible max or min. It could be a level spot. I think we talked about those earlier this year. Slope of 0. Okay, but it's a possible max or min, aka a critical point. All right, let's do a second derivative. So we have the first derivative in the box to the left. We want to take the derivative of that equation. The derivative of x is 1, and the derivative of f of x is f prime. Let's go ahead and plug in 2. All right. Somehow we got to figure out the slope of the f graph at 2. Plot the point, draw a tangent line. What might you get as the slope? Can we do that at the top? Let's see, 2 is right here. What's the slope of that line that the point is on? -2. Yep. I mean, you can pick a point before it and after it, maybe the point at the top and the point at the bottom, rise over run, to estimate that derivative. So it looks like we get -1. Can you describe the shape of the g graph based off of that second derivative value? Concave down. G is concave down at the x value of 2. It might be concave up in other spots, okay, but since we were testing this value of 2 and got a negative number for the second derivative, we know it's concave down at that spot. Okay, so I know they're not asking you about that, but we should still be familiar with the relationships between original function, first derivative, second derivative, all those things. Okay, how are we doing? Kind of okay? Iffy? We're going to do more on Monday. Okay, we still have a few more to go over. They'll start to sink in, I promise. The derivative of an integral. Top bound times derivative of top bound minus plugging in bottom bound, derivative of bottom bound. Okay, second fundamental theorem of calculus.